Welcome. A lot of us think that data structures and algorithms are all about arrays, trees, and graphs. But there's this kind of hidden gatekeeper in a lot of technical interviews, and it's basic math. So today we're going to build your math toolkit so you can unlock those tougher problems with a ton of confidence. Okay, let's just dive right in with a bit of a reality check. The source material puts it pretty bluntly. If your maths is weak, your coding rounds will suffer. I know that sounds a little scary, and it's a common fear, but here's the good news. The math you need isn't some advanced calculus. Nope, it's a very specific set of tools, and we are going to master them right now. So, here's our game plan. We're building what I like to call the coder's math toolbox. First, we'll talk about what this interview math gap even is. Then, we're going to add 5 absolutely essential tools. Optimized prime number checks, for speed, then GCD and LCM logic for efficiency. After that, fast power and modulo for handling those ridiculously large numbers, and finally, some crucial digit manipulation tricks that pop up all over the place. First up, the interview math gap. So what is it? Well, it's that super frustrating moment when you totally get the algorithm, you know how to code it, but you get stuck on some small mathematical detail. Trust me, a lot of really strong coders hit this wall. This explainer is designed to close that gap for good. All right, let's grab our first tool for the toolbox. Optimized prime number checks. This is a classic problem. It shows up in so many different forms, and knowing the fast, efficient way to solve it is absolutely key. So let's do a quick refresher. What is a prime number? Well, it's any number that's greater than 1 and has only 2 divisors, 1 and itself. Seems simple enough, right? But checking if a huge number is prime, that can be really slow if you don't know the trick. And here's where the magic happens. The slow, brute force way is to check every single number from 2 all the way up to n-1. But the optimized logic is a total game changer. You only need to check for divisors up to the square root of n. Why? Well, think about it. Factors always come in pairs, right? And one of those factors will always be less than or equal to the square root. That insight saves so much time. And check this out. Here's how that logic translates into clean C++ code. Let's just walk through it. We've got bool is prime int n. First, we handle the edge case. If n is less than 1, return false. Easy. Then look at the for loop. For int I is 2, I times I superior n, I++. See that I times I superior n? That's our square root trick, but it's faster than actually calling the sqrt function. Inside the loop, if n%i equals 0, meaning if we find any number I that divides n perfectly, we know it's not prime and we immediately return false. If we make it all the way through the loop without finding any divisors, well then it must be prime, and we return true. So elegant. So you might be asking, why does this even matter? This isn't just some abstract puzzle. You'll see prime number logic pop up in interview problems all the time, in things like hashing algorithms, cryptography, and all sorts of number theory challenges that interviewers just love to ask. Okay, tool 1 is in the box. Now, for our next tool, we're going to look at 2 concepts that are basically best friends. They always appear together. GCD, the greatest common divisor, and LCM, the least common multiple. Now, to find the GCD, we use this beautiful, super efficient method called the Euclidean algorithm. Here's how it works. You start with 2 numbers. Let's call them A and B. If B is 0, then congrats. A is your answer. If it's not, you just repeat the process, but this time with B and the remainder of A divided by B. It's incredibly fast and it's elegant. And the code? Just as elegant. Look at how short this is. It's a recursive function. We have int GCD, int A, int B. The base case is right at the top. If B equals 0, return A. That's our stopping point. Otherwise, we just return GCD, B, A%B. It calls itself with the new numbers until it hits that base case. That's a powerful mathematical idea boiled down to just 2 lines of effective code. Okay, so once you have the GCD, getting the LCM is super easy. The least common multiple is just the smallest positive number that's divisible by both A and B. And the crucial thing to remember is this formula. The LCM of A and B is simply A times B divided by GCD AB. They're directly connected. And just like you'd expect, the code is dead simple. Int LCN, int A, int B. It just returns A times B divided by GCD of A. You see, it calls that GCD function we just wrote. This really shows how building one good tool in your toolbox can make it trivial to build the next one. All right, tool number 4 is a big one, especially if you get into competitive programming. It's fast power and modulo. This is all about how to calculate enormous powers like 2 to the power of 1,000 without your program crashing or just taking forever to run.
The core idea here is something called fast exponentiation, or you might hear it called binary exponentiation. So instead of multiplying a number by itself n times, which is really slow, O of n, we do something much cleverer. We reduce the power by half in each step. This simple trick drops the complexity all the way down to O of log n. For large numbers, that is a massive improvement.
Let's break down this C++ code. The magic is really in how it plays with the power, which is b. So, long power, long a, long b. We start with a result of 1, then, while b is greater than 0, inside the loop, if b is odd, if b%2 equals 1, we multiply our current a into the final result. And then, here's the clever part. A times equals a and b divided by 2. We square a and we have b in every single step. This process just systematically builds the final answer in logarithmic time. It's a fantastic trick to have up your sleeve. Now, when you're working with huge powers, the results can get way too big to even fit in a variable. That's where modulo comes in to save the day. The modulo operator just gives you the remainder after division, and these properties on screen are your best friend. They let you apply the modulo at each step of a calculation. This keeps all your numbers in a small, manageable range and prevents those dreaded overflow errors.
All right, we're on to our final set of tools, essential digit manipulation tricks. Now, these might look simple, but I promise you, they are the absolute fundamental building blocks for a huge number of interview problems.
Okay, here's your quick reference toolkit. Want to get the last digit of a number? Just use n%10. That gives you the remainder when you divide by 10. Want to remove the last digit? Use integer division, n divided by 10. It just chops it right off. With these two simple operations in a loop, you can do anything. Count digits, reverse a number, sum its digits. Master these two, and a whole category of problems just becomes incredibly simple. So let's look at the code for the most common use case, reversing a number. We start with a rev variable set to 0. Okay, now in each step of the loop, while n greater than 0, we do two things. First, rev equals rev times 10 plus n mod 10. We're taking the last digit of n and tacking it onto the end of our reversed number. Then we chop off that last digit from n with n divided by 10. And we just repeat that until n becomes 0. Simple, right? But so powerful.
So let's step back and look at our completed math toolbox. We've got an optimized prime checker that runs in square root time. We've got the super efficient Euclidean algorithm for GCD and a simple formula to get LCM from that. We've got a fast exponentiation method that runs in logarithmic time, and we've got a handful of must-know digit manipulation tricks. That is a powerful arsenal to take into any coding interview.
And that really brings us to the starting line. You now have the mathematical tools that are absolutely essential for tackling a whole new class of problems in data structures and algorithms. So, the only question left is, you've got the tools. Are you ready to solve the problem?